we'll discuss about the Wheatstone bridge. So Wheatstone bridge is a special circuit that was extensively researched upon by Charles Wheatstone, and hence it gets its name from Charles Wheatstone's surname. A Wheatstone bridge has 4 arms with a resistor in each of its arms, and the 4 arms are connected as shown in the figure. So let's say this is resistance R1, this resistance R2, this resistance R3, and this resistance R4. Now these two paths for the flow of current are further connected to an external arm which is called as the voltage arm or the battery arm. So this is called the battery arm. And there's another path which has a galvanometer connected to it that connects these two paths of current flow, and this path is called as the galvanometer arm. And this arm, since it also acts as a bridge between, let's say, point B and D, this bridge is what also gives this type of a connection or this type of a configuration its popular name as Wheatstone bridge. Now, you know that galvanometers are instruments used to measure electricity. In other words, a galvanometer has to measure all the current that is there, that's flowing through a particular path, but by itself it should not end up consuming some of that electricity and transforming it into energy, some other form of energy. So that's the basic requirement of a galvanometer. So the idea here for a Wheatstone bridge is to somehow balance the 4 resistances such that there is 0 current flowing either in this direction or the opposite direction through the galvanometer arm. So the idea is to balance out these resistors in such a way that there is no current flowing through the galvanometer arm. So if that's the case, then let's say the current flowing here is IG, because it's the galvanometer arm. I'll call it IG. Let me call this as I2, which is current flowing through R2 resistor. There's current here which is I1. There's general current I flowing here. Let's say this produces a voltage difference in the circuit of voltage V. There's current I4 being flowing through the arm BC, and finally you have I3 flowing over here. Now if I apply Kirchhoff's current law or the junction law that we discussed previously to, let's say, this junction, then I would get I2, which is current flowing into the junction, to be equal to the currents flowing out of the junction. Similarly, if I apply the same junction law to point D, I will also get I1 equals, so I1 plus Ig, which is also flowing in, to be equal to I3. But we started off our discussions by saying that the current flowing through the galvanometer arm is to be set in such a way that it is 0, which means I take Ig to be 0. In which case, both these equations now reduce to I2 equals I4 and I1 equals I3. So I have summarized our findings till now in the box over here. So we got I1 equal to I3 and I2 equal to I4, given Ig is equal to 0. Now let's try and apply Kirchhoff's voltage law or the loop law to the two loops that we see here. So one loop is A, B and D, the other loop is B, D and C. So if I consider the conventional direction to be clockwise here, then applying it to loop A, B, D, I get I2 R2 because it's in the direction of the flow of current plus Ig into the resistance of the galvanometer. So let me take it as Rg minus I1 R1 to be equal to 0. Similarly, Ig, we have already assumed it to be 0, so this term becomes 0. So I am left with I2 R2 to be equal to, I take this to the right side, I get I1 R1. If I take R2 that side, I am left with I2 by I1 equal to R1 by R2. So applying loop law, we end up getting I2 by I1 equals R1 by R2. Similarly, now let's apply the loop law to the second loop, which is B, D and C. So again, I take this to be the direction. So I get I4 R4 minus I3 R3 minus Ig Rg equal to 0. Similarly, Ig is already, we have assumed the current flowing through the galvanometer arm to be 0. Hence, Ig is 0. So that leaves us with I4 R4 equal to, I take this term to the right, I get I3 R3. So again, I bring I3 this side, so I am left with I4 by I3 equals R3 by R4. Now, let's compare the results we have got so far. So, comparing the results we have obtained so far, we have got I2 by I1 equals R1 by R2 and I4 by I3 equals R3 by R4. and we also know I1 is the same as I3 and I2 is the same as I4, which means I2 is the same as the current flowing here. The current flowing through this arm is the same as the current flowing through this arm. The current flowing over here is the same as the current flowing over here. So that leads us to a simple conclusion, that's I2 by I1 equals I4 by I3, which is equal to R1 by R2, which is equal to R3 by R4. I just take this part of my results and what I get is R1 by R2 to be equal to R3 by R4. So taking R4 to the left hand side and these two terms to the right, I get R4 equal to R3 R2 divided by R1. So what's the significance of this result? You will discover that if R4 is an unknown resistance, if it's an unknown resistance, then I can use this equation and assuming that I have made the Wheatstone condition, or what we can also call the balance condition, to be true, then I can use this equation to find out the unknown resistance. So whenever I have four resistances of which one is unknown, I can connect it over the arm BC, and then I can keep one of these resistors as a variable resistor and go on varying it till I achieve the balance condition. What is the balance condition? The current through the galvanometer arm is 0, and I will get to know that it becomes 0 because the attached galvanometer will show null deflection. At that point, I find out what is R3, which is the variable resistance. I already know what is R1 and R2, and that leads me to find out what is the resistance of the unknown resistor. So my Wheatstone network can be modified to support this. So I can change this particular resistor to be a variable resistor, and this resistor to be the unknown resistor. So the Wheatstone network will help me keep varying this resistance till the current through the galvanometer is 0. At that point, I take the values of R2, R1 and R3, use the equation I have got to determine what the value of R4 is.